Hello, and welcome to episode 4 of the Ropeway Center Report. I'm Billy, and thanks for joining me. Today's topic is Ropeway 101 Part 2, Ropeway Components. We're going to go through all of the components on a ropeway today and basically take a peek under the hood for how a ropeway really works. Dr. Yosef Nejes has created a grouping system for ropeway components that will be used today. The 7 groups used are carriers, ropes, line gear, station mechanical equipment, station electrical equipment, station structures, and evacuation equipment. We'll go through each of these component groups today using examples, diagrams, and plenty of images to explain what is going on. Most of the images used are my own personal images. However, I did use some outside sources and sources from the Information Center for Ropeway Studies, which are given at the very end. Please note that most of the components talked about today will be talked about in the context of monocable circulating aerial ropeways. I will go in a little bit to different types of ropeways, aerial trams and funitels and surface lifts, but that's the main focus of this presentation, to explain components for monocable circulating ropeways. All right, let's jump right in. We'll start with carriers. Carriers are what takes up a load on a ropeway, whether that load is passengers or materials. Carriers come in many different shapes and sizes depending on the application and location of a ropeway. First, we'll talk about gondola cabins. Gondola cabins are enclosed vehicles which are used to transport people in either seated or standing capacity. Here are some important components of gondola cabins. The cabins themselves can either be level walk-in, where the surface is flush with the load or unload surface and passengers just walk straight in, or there's a small step up from the loading or unloading area into the cabin. The suspension will damp out any vibrations or bumps in the line and make the ride smoother for passengers. The hanger arm connects the suspension to the grip, and the grip is what connects the entire assembly to the haul rope. We'll talk about grips more in a little bit. Lastly, the door open mechanism opens and shuts the doors in the terminals and ensures that the doors are fully locked. These are close-up images of that door open mechanism. Both are shown in the door locked position. As the cabin approaches the point in the terminal where it is to unload, a metal rail will push this roller upwards, and now we'll unlock the door. When it's time to close, this rail, another rail with the opposite shape as one can imagine, will push the roller back down to this position, and the door will be locked. Chairs are another type of carrier where the passengers sit on a bench-type device while they are riding the ropeway. Chairs can either be fully open and exposed to the elements, or have a shield, a plastic shield, to protect the riders while they are riding, that is known as a bubble. Here are some important components of a chair. Note the similarities to a gondola cabin with the grip and hanger arm, although the hanger arms will be different shapes for chairs than for gondola cabins. The taco is the component of the chair that connects the hanger arm to the bail, which is the frame of the chair. The taco will often have a vibration dampening device in it to make the ride smoother for passengers who sit on the seat, which is shown here in the flipped up position. There's also a comfort bar that provides a sense of safety and can also have optional footrests for passengers. There are some slight differences for bubble chairs. First, there is a bubble open and close mechanism that is very similar to a gondola cabin door open mechanism, which is used to automatically raise and lower the bubble in the lift terminals. Second, there are 2 points of attachment from the hanger to the bail. This allows for much greater vibration dampening and a smoother ride for passengers. Other types of monocable carriers include cabriolet cabins, which are open-air style gondola cabins in which the passengers must stand, as shown in the image on the left, and materials transportation carriers, as shown in the image on the bottom right in the example of ore transportation at a mine. Note that materials transportation carriers will have many different shapes and forms based on the material that they are transporting. The image on the top right shows a combination lift, nicknamed a chondola, in which chairs and gondola cabins run on the same line. A unique terminal setup is required to make this possible. As shown here, carriers on other types of ropeways can have many different shapes and forms, from simple T-bars and platters on surface lifts, all the way up to the largest aerial tram cabins and funicular vehicles that can accommodate hundreds of people, both sitting and standing. The grip is the ropeway component that attaches the carrier to the haul rope. There are 2 main types of grips as we discussed in our last video on the tree of ropeways. Fixed grips are designed to attach securely to the haul rope in one location and not move during normal operation. The most common type of fixed grip is the frictional grip, which uses a movable jaw and a fixed jaw to clamp down securely onto the haul rope. This is shown in the top image and diagram. Another type of grip is the insert clip grip. This is more rare, in which a positive grip is inserted into the strands of the haul rope. This is shown in the diagram and image below, and was popularized by the U.S. lift manufacturer Ropeway. Detachable grips are designed to detach from and reattach to the haul rope, allowing for carriers to be slowed down for easy loading and unloading in the lift terminals. Grips can either be in the open position, where the jaws are larger than the diameter of the haul rope, or in the closed position, where the jaw is the exact diameter of the haul rope so that it can be attached. Single position grips have one default setting, where the grip is closed. The grip will only be open during the period where the carrier is detaching or reattaching to the haul rope. Double position grips have two default positions. The grips can be closed when they are on the haul rope, and when they are traveling around the terminals, they stay in the open position. Here are some important components of a detachable grip. The grip shown is a Leitner-Palma LPA single position grip. The grip wing sits on top of the haul rope when the grip is attached and smooths out the transition with depression sheave assemblies. The traction plate transmits power from rotating tires in the terminal tire banks to allow the grip to move, which it rolls on running wheels which roll along a small grooved track in the lift terminals. Coil springs provide the adequate force to keep the grip jaws locked securely onto the haul rope without slipping. The grip jaws are opened and closed by the actuating roller, where a beam in the terminal will push down on this actuating roller to open up the jaws. The guide roller ensures that there is no rotation of the grip around the axis of the haul rope as the grip is entering the terminal, which could cause some problems if the grip enters the terminal incorrectly. Lastly, this lift has heated seats, so in this case a power channel is used to charge up the batteries for the heated seats when the lift is in the terminals. We'll go over how the detaching mechanism works later, but for now it's just important to understand the grip terminology. This is a better view of the jaws on a detachable grip. The grip shown is a single position grip in the closed position. There are two jaws, the fixed jaw, which stays in the same place the entire time, and the movable jaw, which is pivoted to open and close on the haul rope. Force to keep the movable jaw locked securely onto the haul rope comes from the coil springs, which have a force in this grip acting in this direction as shown. This is transmitted through the actuating arm to the movable jaw via a grip jaw axle that is not visible here. To open the jaw around the haul rope, the actuating rail in the terminal will press down on the actuating roller, which will press down on the actuating arm and compress the coil springs to open up the jaws and allow the grip to be detached from the haul rope. These are some grips found on other types of ropeways. The image on the top left is a bicable detachable gondola grip. Note that it looks very similar to a monocable detachable grip, except with carriage wheels attached to glide along the track rope. The image on the top right is of an aerial tram carriage. This will contain the fixed grip for the tram's haul rope, as well as carriage wheels to glide along the two track ropes for the tram in this case. The bottom image is of a fixed grip for a funicular system. Note that the haul rope is wrapped several times around the grip for necessary friction. Let's move on to our next component group, which is ropes. Wire rope is defined as the helical arrangement of steel strands around a core. Wire rope provides the suspension and movement for ropeway systems. There are many different applications for wire rope in industries around the world. Today, we'll just be talking about wire rope for use in ropeway systems. The haul rope provides motion to the carriers. In this type of wire rope, the strands are composed of individual wires that are also wrapped in helical orientation. The strands are then wrapped helically around a core, typically a fiber core. All of the images on this slide are 6-strand wire ropes. However, 7-strand wire ropes are also common for ropeway haul ropes. Here are images of stranded wire ropes on two different ropeway systems. See if you can spot the difference between the strands and the individual wires that compose the strands. The haul rope is required to be an endless loop that can be rotated seamlessly to move the carriers. Obviously, if there was a knot or connecting device in the middle of this loop, it could cause some operational difficulties for the ropeway. The haul rope has to be a constant diameter throughout. So how is this endless rope loop formed? This is a process called the long splice, or nicknamed tying the knot. This is a process that is carried out by some very skilled tradesmen, all completely by hand. I'll try to go over it here at a very entry-level view in this video. The first step is to detension the rope and lower it down from the towers onto wooden pedestals called sawhorses so the work team can work easier. First, some of the strands are unwound from the wire rope. This is shown in the image on the right, with 3 downhill strands unwound. This is done by passing the strands over and under the wire rope to make sure it does not get tangled. The image on the bottom left shows a section of wire rope with a strand missing that has been unwound for part of the splicing process. The image on the top left shows the marriage, which is where the 2 ends of the wire rope meet. The strands that have been unwound are then laid on top of the opposite sections and then wound back in together to form the endless loop. The white segments of core are shown sticking out, forming that X shape from both ends of the wire rope. The man in this image is Mr. R.J. Knight from Knight Equipment Company, a world-renowned wire rope splicer. You can find more information about his company at knighteq.com. That's Knight with a K. This is a diagram from Dr. Gabor Opłatka showing the long splice in wire rope. After the strand has been wound back into the wire rope, in order to maintain the constant diameter, it will be tucked back into the center of the wire rope. This is called the tuck and is shown in the image below, circled in red. The tuck effectively replaces a small section of the core. The friction between the outer strands and the tuck prevents the tuck from being torn out under tension. You can think of it like a Chinese finger trap. The more tension there is on the wire rope, the stronger the friction, and the stronger the overall splice. Overall, when the process is done, the wire rope looks seamless, and only the small tucks are evidence that there is a splice here. This process can be kind of confusing, so don't worry if you don't understand it on the first go-around. And I've heard it nicknamed in the industry as rope magic, because once you're done, you have no idea that that rope started out as anything but an endless loop. Bi-cable and tri-cable ropeway systems have additional ropes other than the haul rope that are used to provide extra suspension in between towers. These are called track ropes and are composed of locked coil wire ropes. This is a unique arrangement of helical, Z-shaped interlocking wires around a traditional wire rope strand. This creates a smooth outer surface of the wire that allows wheels to easily glide over them from the carriages of bi-cable and tri-cable carriers. These ropes are stationary as opposed to moving haul ropes. The next component group we'll discuss is line gear. Line gear is all of the mechanical systems and components that support and guide wire ropes, either track ropes or haul ropes, in between the terminals on a ropeway. Towers are the structures that support the haul rope on a ropeway to make it the required height, as designated by engineers. Here are the important components of a ropeway tower. The foundation is a large piece of concrete that anchors the tower solidly to the soil. The tower tubes on most modern ropeways are hollow cylindrical tubes made of steel. A service ladder is how maintenance personnel accesses the tower from the ground and includes an ascending system to keep the maintenance workers safe. The crossarm is the steel piece that runs perpendicular to the top of the tower tube and has the shiv trains on either end. The shiv trains are the wheels that the haul rope runs in for the ropeway. Shivs are what the wheels are called. The line gauge is the width between the 2 sides of the haul rope. Lastly, the lifting frame is this square frame that you see here that lift maintenance personnel will use when they need to lift the haul rope off the shivs to inspect the shivs or replace them. These are the different types of tower styles. On the bottom left, we have a tubular cylindrical tower, like the one shown on the previous page. In this picture, the tower is one large piece of cylindrical steel. However, several different tower segments can be used and bolted together at flanges to make the construction process easier for larger height towers. On the top left, we have a portal tower, where there are 2 tower bases and the steel infrastructure meets in the middle to house the shiv assembly. The carriers pass through this portal. On the top right, we have a tapered tower, where the radius of the tower increases as you get closer to the ground. This helps offset the increased bending moments that are created towards the bottom of the tower. On the bottom right, we have a lattice tower, in which a steel framework is used to create the tower shape instead of a tubular or tapered piece of steel. This is used for towers that have much higher loads and are commonly found on larger ropeway systems such as aerial tramways or tri-cable ropeways. These diagrams show some various different aspects of shiv trains. Shivs come in pairs of two that are connected with a bracket called the evener frame. The evener frames are then connected to the main frame of the shiv train. This allows the shivs to move in such a way that creates the desired curve for the haul rope smoothly over the towers. There are two types of shiv assemblies shown here: support shiv assemblies and depression shiv assemblies. Support shiv assemblies have the haul rope on top of the shivs and are used to elevate the location of the haul rope above where it would normally be without a tower. Depression shiv assemblies are the opposite. The haul rope is located below the shiv assemblies, held up by tension, and is used to lower the position of the haul rope relative to where the tension would want it to be if there was no tower. The image on the right shows one of these depression assemblies, also known as hold-down assemblies to those in the industry. The image on the left shows a compression or combination assembly. This shiv train has shivs on top of and below the haul rope, and is used for towers that are very lightly loaded or towers that have fluctuating loads due to factors such as how much the carrier is loaded relative to its capacity and wind. These are some images of shiv assemblies from up close. In the image on the top left, note how the evener feeds into an intermediate bracket which feeds into the main frame. This is commonly used on shiv assemblies with a larger number of shivs. In the image on the top right, note how all of the shivs have a grooved rubber liner that the haul rope sits in and runs in. This liner will wear out normally over time as the ropeway is used, and is the reason why shivs on ropeways need to be replaced in what is called line work. The image on the bottom left shows that the lifting frame has different cables also attached to it in addition to the haul rope. These cables do not move and are known as the communications lines, which are part of the electrical equipment of the lift that we'll talk about later. Lastly, the image on the bottom right shows the maintenance catwalks that are present on some towers, which are used by maintenance personnel to easily access the shiv trains and perform their work. An important component of line gear is the rope monitoring equipment. This is used to quickly alert operators and maintenance personnel if there is a situation that could cause a derailment. A lift that moves fast enough has to have a primary monitoring system and a backup monitoring system. The primary monitoring system for Leitner Palma and Doppelmayr lifts is shown circled in red. Here, proximity sensors are used to detect where the haul rope position is exactly and stop the lift automatically if it is outside of this position. The backup system on both of these lifts is shown circled in yellow. These are known as brittle bars and are engineered so that if the haul rope slips completely off of the shiv assemblies and the primary system fails, a metal bar that has current running through it will break, the current will stop, and that will trigger a stop in the lift controls. As you can imagine, line gear is highly specific to the type of ropeway you're working with. Some examples are given here. On the top left, there are the tracks and deviation shifts for a funicular. The top middle shows a tower on a 3S gondola. The top right shows a tower on a funitel system. And the bottom left shows a slat carrier, which is used on an aerial tramway or tri-cable ropeway. The next component group is station mechanical equipment. This includes all of the mechanisms that power a ropeway, keep the haul rope under tension, and detach the grip for detachable ropeways. We'll start with bull wheels. Bull wheels are large metal wheels at the terminals of ropeway systems that are used to redirect the haul rope. They can either be drive bull wheels, which are powered, or return bull wheels, which simply spin to redirect the haul rope. On many fixed grip lifts, the bull wheel will be exposed. However, on detachable lifts, the bull wheel may be obscured by detachable terminal cladding. The diagram on the top left shows some important components of a bull wheel. Note that there is a grooved rubber liner for a bull wheel that's similar to a larger version of the liners found on shiv wheels. The drive is what powers the ropeway. See if you can identify the components from the diagram on the right with the image of an actual ropeway drive setup from a fixed grip ropeway on the left. The general concept is as follows. An electric primary motor will spin a drive shaft at a very high RPM that feeds into a gearbox. The gearbox will have an output shaft at a lower RPM or angular speed and a much higher torque that is provided to the bull wheel. A backup auxiliary drive unit, typically diesel powered, is on standby in case there is a problem with the primary electric mover. The image on the right shows an example gearbox, while the image on the left shows some gears that had been removed from a very similar gearbox for preventative maintenance purposes. Note in this gearbox that power enters from the primary electric mover or auxiliary motor here and leaves to the bull wheel at a higher torque and lower speed here. This gearbox also accomplishes a 90-degree direction change for the power. Gearboxes are a critical component for ropeway systems, both because of the necessary speed reduction for most primary electric motors, and because there is often no good way for redundancy for a gearbox system if it were to fail. Thus, over-engineering is critical for gearbox components. Note the large industrial roller bearings that are used on these gears. An overhead drive on a ropeway is where the drive setup is located in an engine room in the terminal above the bull wheel. This is an interesting overhead drive setup on Gondola 1 at Vail Mountain. This lift uses a total of 6 electric motors to move the lift. There are 2 primary and 2 secondary motors that have inputs to the gearbox. You can see one input shaft right here with the cover removed, and the other 3 have inputs right here on a component called the splitter that feeds into the gearbox. The 2 tertiary motors are a little bit harder to spot. Here's one. They are connected to the bull wheel directly via a ring and pinion system. This means that the lift can move in any combination despite gearbox failure, electric motor failure, or even power failure, since there are backup diesel generators for the lift. On the other hand, a vault drive has the drive setup located in a basement-type room below a ropeway terminal and a connecting drive shaft that will go up through the floor of the terminal and power the lift. This is a vault drive on Gondola 19 at Vail Mountain, the Eagle Bond gondola. The 2 electric motors are the leader and follower electric motors that feed into a splitter, which directs the power to the gearbox and up through the drive shaft to the bull wheel. There are also a tertiary drive with a ring and pinion setup. They're located directly on the bull wheel. Backup power is achieved through this ring and pinion setup or via diesel generators in case of power failure. The last note about drives is direct drive technology. In this setup, which is relatively new to the industry, a low-speed synchronous motor sits directly on top of the bull wheel and spins at the same speed as the bull wheel to move the lift. There are no gears because of this direct connection, so there are no friction losses or noise from a gearbox system. This setup is thus quieter and more energy efficient than traditional drive setups. There are typically 3 types of brakes on a ropeway: the service brake, the emergency brake, and the rollback brake. All brakes for a ropeway are a normally closed setup, meaning hydraulics are needed to pump up the brakes, separate the calipers, and allow the lift to spin. If there were any sort of hydraulic failure, the calipers would close and the lift would not be allowed to move. The service brake, which is shown on the right, is what is used to stop the lift during normal operation. This is applied directly to the flywheel. The emergency brake and rollback brake are rather applied directly to the drive bull wheel to stop the lift. The difference between the two is that the emergency brake and service brake will have a button on the control panel, while the rollback brake will be deployed automatically. A rollback on a lift is where a lift unintendedly spins in the wrong direction versus the way you are trying to run it. This is obviously a very dangerous situation, so there are many engineering devices that are employed to prevent this from happening. Rollback brakes will be deployed automatically if the lift senses a rollback. Another common rollback prevention device is a high-speed backstop that is employed on a flywheel. Drives on other types of ropeway systems can vary widely. The image on the top left shows a drive setup for a jigback aerial tramway. In this vault drive, there is a unique haul rope configuration around 2 bull wheels to create the required friction for the electric motor to spin the lift. The image on the top right shows the drive for a T-bar surface lift. The entire drive is located in the small enclosure directly below the bull wheel. This is a very simple and cost-effective solution. The diagram on the bottom shows the drive setup for a Funitel system. The haul rope is deflected through the terminal into the vault, where 2 electric motors are synced to a unique bull wheel setup that creates the parallel haul rope configuration required for a Funitel. Tension in a wire rope is the axial force that is transmitted through the rope. Correct tension is required on the haul rope and the track rope systems for the required friction and heights of the cable systems to support the loads. These will be designated by the engineers who build the lift. A very simple system to provide tension is called a counterweight, which is where a large tension is provided through a large mass that is suspended in the air at the tension terminal of the lift, shown in the image on the left. The return bull wheel will glide on a carriage whose position will be adjusted based on the mass of the counterweight and the load of the carriers on the line. The image on the bottom right shows a counterweight pit on a jigback aerial tramway system. This is used to provide the required tension for the track rope systems. Most modern ropeways will use some form of pneumatic or hydraulic tensioning for the lift. In both cases here, you can see the hydraulic rams shown with red arrows in the image on the top left and circled right here to provide the required tension for the bull wheel, which is still moving on a carriage. Now let's talk about detachable mechanisms. We've talked before about the components of a detachable grip. Now we'll learn how they work with the mechanisms in a terminal for detachable grips to operate. This is a grip that is being opened in order to go back onto the line. Note how the actuating rail is pushing down on the actuating roller to open up the grip jaws. The running wheels are running in the running rail that provides a track for the lift, and the guide rail is ensuring that there's no tilt or rotation of the grip as this process is occurring. This is an overview of a detachable terminal layout. Note that this whole terminal can be mirrored around a plane or line through this angle, and the process is all very similar, but located in reverse. I'll explain that here. A carrier will enter through the grip opening zone, where it is quickly detached from the haul rope. In the deceleration zone, the grip is slowed from line speed to terminal speed. The turnaround is the grip moves at a constant speed and will turn around through the running rail and tire banks. After the carrier has been loaded or unloaded, it will speed back up through the tire banks in the acceleration zone and then quickly reattach to the haul rope in the grip closing zone before it goes back onto the line. Note that the grip closing zone and the grip opening zone happens very rapidly. This is not a gradual process, so that there is not any dragging of the jaws on the haul rope as it is being detached. This would damage the grip jaws and the haul rope. The image on the top left shows a grip that is being reattached to the haul rope. Note that the jaws are open and the haul rope is being deflected into the correct position for reattachment. The other images on this page all show different types of grips passing through the terminals via tire banks. The tire banks provide the motion for the grip when it is not connected to the haul rope. Power is transmitted from the tire banks to the grip through the traction plate. These tires can either be pneumatic and filled with air or solid rubber. The tires in the tire banks are powered via a direct mechanical connection to the haul rope called a power takeoff or PTO system. The haul rope will spin large PTO sheaves that are connected to several tires in the tire bank via a grooved rubber belt called the PTO belt. All of the other tires in the tire bank are then connected to these two tires via rubber belts. The acceleration and deceleration regions are created by adjusting pulley ratios to move the tires faster or slower relative to one another. The advantage of this system is that since it is directly tied into the haul rope, the speed of the tires will always be proportional to the speed of the lift. The image on the bottom left shows the rubber belt connection between tires in a tire bank. The image on the top left shows a contour chain, which is used for the turnaround on many older detachable ropeways. After the straight portion of the tire banks, the carrier hanger is captured in the teeth of the chain and moved around the turnaround. A similar setup is often used for detachable ropeways with a midstation. The image on the right shows a spacing system for a detachable ropeway. This ensures that all of the carriers are properly spaced apart and uses a set of tires that are powered independently by a spacer motor rather than connected to all of the other tires via the PTOs. A sensor system will detect if the carriers are spaced too close together or too far apart and will speed up or slow down these tires as necessary to adjust the position of the carrier. Now that we've talked about all the aspects of a detachable terminal and the detachable mechanisms, let's watch this video of a grip being detached from the haul rope to put it all together. The station electrical systems comprises a wide range of equipment that includes control systems to power the ropeway and sensor systems to ensure that the ropeway is operating safely as expected. The electrical drive is the heart of a ropeway's electrical control. It will tell the primary electric mover what speed to move at and control its overall operation. The diagram on the left shows a general concept of what's going on with an electric drive. It will take inputs from monitoring devices, both on the line and in the terminals, and inputs from the consoles and other controls for the ropeway, and input them into a PLC or programmable logic controller. Here, a combination of electrical hardware and software systems will tell the primary electric mover exactly what to do. The image on the center shows some example drive cabinets for a ropeway, and the image on the right shows the inside view where you can see some of the relays for a ropeway electrical cabinet. We've talked before about sensing devices in shift trains out on the line of ropeways. Now we'll talk about some sensors and monitoring devices in terminals. This is a diagram of some sensors and monitoring devices in a ropeway detachable terminal. Note that for basically every function as the grip goes through the detachable terminal, there is at least one sensor to monitor it, if not two for redundancy. The image on the left shows some proximity sensors, which are part of the anti-collision system. These sensors are triggered when the grip passes over them as it is traveling through the terminal. The sensors will send that signal to a computer system, and the computer system will determine if the grips are too close together and send a stop command to the controls if so. The image on the right shows a grip profile switch. This is a paddle that will get triggered through direct contact with the grip if it is not connected 100% correctly with the haul rope, and send a stop command to the controls. The rope position switch acts in a very similar way. If the haul rope drops too low for some reason in that portion of the terminal, then it will contact the paddle, push it down, and a stop command will get sent to the lift. A different example of a proximity sensor is also shown in this image. These are some examples of ropeway controls at the drive operator console in the lift operator house. A more streamlined version of the controls can be found at the return terminal and in operator pedestals located around both terminals for ease of use for operators and maintenance personnel when they are standing outside. Although the specific layout of the controls may look different for all of these lifts, the overall function is actually pretty similar. You will have two stop buttons, a normal stop and an emergency stop, a slow, medium, and a fast button, and a start button and a reset button. If a lift is stopped, the procedure will be to pull the stop button back out, get a reset from both terminals to reset the stop or fault, and then hit start at the drive terminal. The output for all these controls looks slightly different. The image on the right is the lift built in the 80s, and the image on the bottom left is the lift built in 2012. As you can see, the output changed from a system of lights to a modern touchscreen system that can also show wind speed and many other features of the lift's operation. Aerial tram controls are notably different than other types of ropeway controls, largely because the operator will also ride up in the carrier along with the passengers instead of just being stationed at the top and bottom terminals. The image on the right shows that for aerial trams, there is a main control operator desk where attendants will sit and monitor the main functions of the tram from the ground. The image on the left shows that there is also a control system in the tram cabins themselves. Here the operator can open and close the doors of the tram, as well as slow down or speed up the line speed based on factors that is mostly wind speed to adjust to prevent sway of the cabins. They can also, on some trams, deploy track rope brakes, which are like an emergency braking system that attaches onto the track ropes if there is some sort of catastrophic failure with the haul rope. The next component group is station structures. These are the buildings that are necessary to house all of the equipment in a ropeway terminal, such as drive systems, tension systems, electrical controls, and detachable mechanisms. Fixed grip station structures are relatively simple, both to save on costs and fit in a smaller overall footprint than detachable ropeways. Most drive setups will be an overhead drive with a motor room, such as the image on the left, although vault drives on older ropeways are also common for fixed grip setups. The image on the right shows a return terminal for a fixed grip ropeway. Note that the bull wheel here is fixed in place, meaning that the other terminal will have the tension and drive systems. Open-air detachable terminals are a type of station structure that protects all of the important mechanical components from the elements, while also allowing passengers to load and unload the ropeway outside without having to enter or exit large buildings. Some important components of detachable terminals include this component right here, which is circled and nicknamed the trumpets. These are the entry and exit points for the guide rails, and the tower masts, as shown here on the arrows, which support the load of the terminal. For a tension setup, the bull wheel needs to move back and forth. This is accomplished in open-air detachable terminals in one of two ways. Either there is an internal carriage where the bull wheel is moved back and forth on a set of rollers, or the entire terminal will move on a set of rollers attached to the terminal masts. On the other hand, enclosed detachable terminals are a station structure that uses a large building to protect the terminal equipment from the elements. These are typically used when an open-air terminal structure would not be suitable for the ropeway. There are two reasons why this could be. First, the ropeway terminal equipment specific to that ropeway might not fit well or neatly into an open-air standardized terminal design. In this case, the enclosed terminal provides more space and overall design flexibility for the engineers. Second, the customer might desire a unique aesthetic component to their terminal design and want a different look than the open-air terminal design. Note that the terminal equipment, such as the tire banks, is exposed and able to be viewed by the passengers of the ropeway, which is unique compared to open-air terminal designs. Here are some unique station structures that differ from traditional open-air or enclosed terminal structures. The image on the left shows a chairlift at Vail Mountain in Colorado that is built to mimic a rustic barn. The image on the top right shows a detachable gondola terminal at Disney World in Florida that was built to match the French theme of that area of their theme park. The image on the bottom right shows an 8-passenger chairlift terminal at Big Sky in Montana that features a large LED video board to display messages on. Detachable ropeways can also have mid-stations where the carriers will detach from the rope along the line to provide an additional point for loading or unloading different than the end terminals. Depending on the type of ropeway, this mid-station can have many different formats. In the images shown here, a small change of angle is accomplished at the mid-station, and the haul rope runs through it, as shown with these deflection shivs right here. Other types of mid-stations will use two different haul ropes with a same shared bull wheel that will transfer the power via friction. Other types of ropeways will actually be two separate ropeways mechanically that will meet at one mid-station, and this can be used so that one section or another can be run depending on the different operational needs. On ropeways with gondola cabins or bubble chairs, a carrier parking facility may be used to house the carriers and shelter them from the elements when the ropeway is not in operation. The carriers will be removed from the line through an offline rail, as shown here. In this image, the carriers are being added back onto the line through the terminal on the online rail. Once in the facility, the carriers are protected from the elements, and maintenance personnel can also work on them in separate maintenance bays. This is an example of a carrier parking facility at Gondola 1 at Vail Mountain in Colorado. The station structures and other types of ropeways will vary highly depending on the needs to house the different types of ropeway equipment and the aesthetic demands from the customer. Starting from the top left and going clockwise, we have a top terminal station structure for a monocable jigback tram, a bottom terminal station structure for a tri-cable jigback tramway, a top terminal station structure for a Funitel system, and a terminal structure for an aerial people mover system. Our last component group is evacuation equipment. This includes all of the components and systems that make sure passengers can always disembark a ropeway safely, no matter what components may fail from other groups. I want to note here that ropeways have a very high safety track record, and the industry places a very high emphasis on safety. The evacuation equipment is a necessary redundancy with a very low likelihood of ever being needed. Auxiliary drives are used to provide power to the ropeway in case of failure with the primary drive setup. The image on the top right shows a setup where a diesel motor is used to provide input to the gearbox in case of a failure with the primary electric motor. Note that this specific image, the ropeway does not use a disengageable V-belt, but rather a splitter on the gearbox that can take input from different components. Here, the gearbox is still used in both setups, so the ropeway would not be able to move in the case of gearbox failure. The image on the bottom right shows a different setup where the auxiliary drive uses a diesel motor to power a disengageable hydraulic motor that is connected to a ring gear on the bull wheel of the ropeway. This is known as a ring and pinion setup and does not rely on a gearbox, so the ropeway can be still moved in case of failure with the gearbox. The image on the bottom left shows the most comprehensive auxiliary drive setup currently used on ropeways. It uses detachable couplings with several different drive setups as well as emergency bearings to ensure that no level of gearbox failure, power outage, or drive failure could prevent the ropeway from being moved to evacuate all of the passengers. Redundancy and reliability are critical aspects for any ropeway component. However, in the most extreme and emergency situations, a full evacuation may be necessary. A rope-down evacuation is a process where trained personnel will reach the stranded carriers using the haul rope and use our system of ropes to safely lower passengers to the ground. In cases where this is far too high off the ground to be possible, a rescue ropeway is built along with the ropeway. This is a system where a reversible ropeway or a simple system with a winch drive is used to allow a carrier to reach the stranded carriers. That will allow the passengers to offload into the rescue ropeway carrier and reach the ground safely. These are the works I used to supplement my own knowledge and put together this presentation. The work done by Dr. Archer Doppelmayr and Dr. Josef Nedjes is very valuable to the industry and was very helpful to put together this presentation. I took most of the images I used to put this presentation together myself. However, if there was a small number located within the image, it was an image that I found online or through the Information Center for Ropeway Studies to help put this presentation together. Here's the sources for all those images in case you're interested in learning more about them. Thank you very much for joining me today. I hope learning about ropeway components gave you some insight into how these incredible machines really work. A couple thank yous are in order for this episode. First, thank you to everyone at the Vail Lift Maintenance Department. I took most of these photos during my 2 summers working for the Vail Lift Maintenance Department, and everyone on staff was very nice, took lots of time to help me have hands-on experiences and teach me many things about ropeways and lifts, and I'm very grateful to that. So thank you to everyone with Vail Lift Maintenance. Second, thank you to Peter Landsman and liftblog.com. I used photos from Mr. Landman's website to fill in some of the gaps where I didn't have a good photo of a ropeway component. So thank you to Peter Landsman, and make sure to go check out his website, liftblog.com. Thank you once again for joining me today. I hope you'll join me for episode 5. We'll cover the history of ropeways from ancient origins to the modern day machines we see today. I'm excited for that, and I hope you'll join me then. See you next time.